So let's start today's class. Computer Organization, Module 1, Lecture 5. Okay. Now, see here. Today, in this lecture, we will learn about the different number systems used in a machine. Okay. Now, I have already sent you a notes. In the notes, I have given how to convert one number system to another. Here, we will just recall those things and go to the another things. That means for how to represent the number in fixed point and floating point. So number system in generally in computer, there are these types of bases are used. They are the base 10, base 8, base 16, and binary. That means base 2. These are the number system generally used in a computer system. Now you already know that base 10 system, generally the number we used in our everyday life is the base 10 system. Now suppose what is the base 10? How to represent the number in the base 10? Suppose this number is 1734. This number in the base 10 representation will be from the right hand side. That means called the that means here 4. So 4 into 10 to the power 0 plus, as the base is 10, 3 into 10 to the power 1 plus 7 into 10 square plus 1 into 10 to the power 3. So if I add this, we will get 1734, this number. Okay, suppose there is another number which is a decimal point, that means 724.5. The same thing, how to represent in the decimal? That means that after point, for this reason, this is 5 into 10 to the power minus 1, and all the numbers 4 into 10 to the power 0 plus 2 into 10 to the power 1 and 7 into 10 to the power 2. That means from least significant bit to most significant bit. Clear? Now this is the base 2. We all know that binary number has the base 2. Then why we represent the number in the base 2? Because computer only understand the high and low, that means 1 and 0. So any number at the inside the machine, that means after the object program is generated, it is transformed into the binary number. Clear? So binary number is required. I have already told you for machine level language. So how to represent the binary into decimal? You know, just recall the thing 10010. This is a suppose binary number. How to represent in the decimal? So 0 into 2 to the power 0, 1 into 2 to the power 1, 0 into 2 to the power 2, 0 into 2 to the power 3, 0 into 2 to the power 4, and 1 into 2 to the power 5. So this is in the transformation of base 2 to base 10. Now here also the same binary number, the same type of binary number, but here there is a decimal point. And in the decimal point, here 0 into 2 to the power minus 1 plus 0 into 2 to the power minus 2 plus 1 into 2 to the power minus 3. And here before the decimal point, 1 into 2 to the power 0, 0 into 2 to the power 1, and 1 into 2 to the power 2. So if I add up, we get the corresponding decimal number. Clear? So this is the from base 2 to representation in the decimal number representation. Base 16, in the notes I have already given that this is called the hexadecimal code. In the hexadecimal code, what is the number? Suppose 8CE. Clear? So 8CE number will represent in this way. That means E into 16 to the power 0. We know that in the decimal number E is 14. C into 16 to the power 1. So C means the 12. 12 into 16 to the power 1. And 8 into 16 to the power 2. That means 256. If I add up, we will get the number in the decimal. So this is a conversion of hexadecimal to decimal number. There is another example. It is the same. Clear? So this is the base 16 to decimal number. Now base 2 to base 16. So base 2 to base 16 number can be easily represented. How to convert from base 2 to base 16? See here. Suppose this is a number which is given in the base 2. Clear? So you take 4 bits, 4 bits, 4 bits, 4 bits. Okay. So that means from right hand side 1110, 4 bits, then again 4 bits, 1100, then again you take 4 bits 1000, these are the 4 bits. You divide it, the total binary number, into 4 bits, 4 bits, 4 bits. So what is this? This is E in the hexadecimal. This is C in the hexadecimal, and this is 8 in the hexadecimal. So the number is hexadecimal is 8CE16. See another example. Here also, this is the binary number. We have to transform the number into the base 18. Here also, see here, we have taken 4 bits from the right hand side: 1001, 0101, 1101, 1011, and 1. Okay. So that means there are 0001. Okay. So first number is 9 in the hexadecimal code. This one is A in the hexadecimal code. Then B. This number is B. This number is D, and this is 1 in the hexadecimal word. This one means 0001. Clear? So this is from base 2 to base 16 representation. Clear? Now base 16 to base 2, the same type of representation, very easy. Suppose this is the A3, A5. This is the hexadecimal code. We have to represent it into the binary code. How to represent? You take 4 bits. That means F means 1111, 3 0011, A 1010, and 5 0101. So this is the binary number corresponding to this hexadecimal code. Similarly, 73EF corresponding to this hexadecimal code, you can find out that this is the base 2 number. Okay, it is the conversion of one base to another. I have given you the notes. In the notes also we will get the same thing. Clear? Now the main thing in the computer system. See, in the computer arithmetic, there are 2 types of representation. You know that arithmetic operations means the summation, multiplication, division, subtraction, etc. For this type of arithmetical operation, 2 types of representation is generally used. One is called the fixed point representation, and another is called the floating point representation. Both representations are very important from the computer organization point of view. Now see here, what is fixed point representation? In fixed point representation, the decimal point is fixed. Clear? Now see here, what is the example of this? See, all the numbers here are fixed point representation. See here, 10.0. Okay. So here the decimal point, this point is the decimal point, this is fixed. You cannot move the point in the right hand side or left hand side. If you move the point in the left hand side, it will be 1. If you move the point in the right hand side, it will be 100. That means value will be changed. So the point is fixed. You cannot move that point. So this is an example. This is an example of fixed point representation in the decimal. This is also the second example is, and fixed point number is a fixed point number in decimal. This is 1001.1101. This is a fixed point representation in binary, and 8AF.3b. This is a fixed point representation in hexadecimal. Clear? You already know what is decimal and what is hexadecimal. So any number, whatever may be the base, one can represent the number in the fixed point. Clear? Now the question is, what is the advantage of using the fixed point number? Previously, when the machine was first invented, or the first computer organization also was actually done, people used the fixed point number. And in our everyday life, you will find that in simple arithmetical calculation or any types of calculation in mathematics, generally we use the fixed point representation. Okay. But what is the advantage? If you want to add 2 fixed point number, you know from school, from our secondary classes or primary classes, how to add 2 numbers. You know how to add 2 numbers in the decimal. Obviously, the same technique can be applied for the binary and also for the hexadecimal code. Clear? So it is very, if you add 2 numbers, 1 by 1 digit you add. If there is a carry, you forward the carry for the next addition. and in this way you add the numbers. This is very easy. As the addition is very easy, it is obvious that the circuit for this fixed point addition will be very easy also. Clear? Now the thing is, what is the problem with this representation? In today's computer, all the modern computers, you can find that they are not actually the fixed point representation. Obviously, the output will get in the fixed point. Suppose in the calculator, you are adding two numbers, or there is a multiplication of two numbers or division. The result will be in the fixed point. But remember that inside the circuit, they are actually used on something floating point numbers. Okay. Now the thing is, if the fixed point number representation is so easy, why machine use the floating point? I will tell later what is floating point, but not fixed point. Okay. Why? What is the requirement of not using requirement of using the floating point number, not the fixed point number? The thing is, there is a problem with the fixed point number. What is the problem? Here, the memory occupation is very large. Yeah. Now, why memory occupation is very large? Suppose this thing, 10.0. Suppose one digit takes 1 bit. Yeah, suppose. So, what is the total number of bits required for this? Is 3 bits. Clear? Similarly, suppose 2, 3, 4, 5, 6, 7. There are 6 digits here. So to represent the 6 digits, we require 6 bits number. If one digit occupies 1 bit, so it is not possible, but just we are assuming it here. Okay. So if I write a very large number, suppose we are writing 1 after 100 0. That means you require 100 0 position. For 100 0 position, you require 100 bits. Okay. And for 1, you require 1 bit. That means 101 bits are required for a fixed point representation if 1, and there comes the 100 bits. Clear? So this representation is very high. Clear? And it will take more memory in the system. And you know, if any number takes more memory in the system, to access that number during programming, processor has to fetch the number from the memory. And if the number is very large, the fetching time will be more. Clear? If the fetching time is more, obviously the performance of the system will be down, because it will take more time to execute one program, which depends upon the fixed point representation. So this is the disadvantage of using the floating point representation. To solve the problem, nowadays people are used another point representation. This is very important. Listen carefully. That is called the floating point representation. Clear? Now, in floating point representation, what is the difference between the fixed point and floating point? In floating point representation, the decimal point is not fixed. Clear? Now, what is the example? See the example I have given here. First example I have given here, 10.23, this number. This number is a fixed point representation. From the representation, you can see this is a fixed point representation. But here, equal to, this is called the floating point representation. Now the thing is, this number is in the decimal number. So here we have written here 1.023 into 10 to the power 1. This 10.23, this is actually 10.23 into 10 to the power 0. Now here, if I move this point to the left, it will be 1.023 into 10 to the power 1. If I multiply 10 here, it will again will get 10.23. Similarly, the same number we can represent 0.1023 into 10 square. If I multiply it, again we will get 10.23. See here, the same number, the point is not fixed. This point is after 0. Again, this point comes after 1. And again, this point comes after 0 point. That means after point, there are 4 digits here. After point, there are 3 digits. Here after point, there are 2 digits. That means this point is not fixed. This is floating. Okay. So this is called a floating point number. This first example is the floating point number representation in decimal. The second example, here you can see that this is a floating point representation in the binary. Clear? Here also 110.11. This is a fixed point, or you can tell is a floating point. Okay, because if you multiply it into 10 to the power 0, it will be a floating point. Now see here, we move the point to the left. That means 11.011 into 2 to the power 1. Why 2 to the power 1? Because here the base is 2. In the previous case, that was the decimal number, base was 10. So we multiply with 10 to the power 1. In the second case, the base is 2. So we are multiplying it with 2 to the power 1. Similarly, if I move it further left here, that means 0.1011. Sorry, I have written here wrong. I think it should be 0.11011. Okay. So into 2 to the power 3. Clear? So the same binary number we have written here as the different floating point representation. Clear? So these are called the floating point representation. So from the example, it is clear that floating point has 3 parts. Clear? One is called the mantissa or M. Another is called the exponent, that is actually the power. And last one is the base, because the floating point representation depends on the base. Clear? So representation of the floating point is plus minus. Plus minus is the sign here, or I have shown here only the plus. If this is minus, you have to give the right here minus. So into mantissa. Mantissa means this part of the system. This part. This is a mantissa. This is a mantissa. Okay. Here 1.023 is a mantissa. 0.1023 is the mantissa. All are called the mantissa. So this part is the mantissa. We multiply it with the base. Base is here it is 10 for decimal. For binary it will be 2 to the power exponent. What is exponent? Here the exponent is 1. Here the exponent is 2. In this case, exponent is 1. In this case, the exponent is 3. So plus minus mantissa, that means suppose here this is the mantissa into base. Base is 2 into exponent E. Here E is 3. Clear? So if I ask you what is the mantissa of this, what is the floating point representation? That means what is the mantissa, exponent and base? Here mantissa is 11011. Clear? Exponent is 2. Sorry, exponent is 1. Base is 2. So this is the floating point representation. Clear? Now, advantage and disadvantage. Advantage of floating point representation is that very large or small number can be represented. Question is how? See here 10.23. Suppose if I take 1 bit for 1 digit, 4 digits are required. Clear? Now here also, in this case, 1, 2, 3, 4. If I represent only the mantissa and exponent, we require 1, 2, 3, 4 and 1 bit. Clear? That means 5 bits. Obviously, it is more here. But if I increase the number of size of the number, clear? In this case, suppose here after 1 there are hundreds. That means suppose we have written 1 after 100 bits. That means 100 bits are required. Clear? But here, if I represent in the floating point number, it will be 1 into 10 to the power 100. So we represent 1 and 10 to the power 100. That means 100. That means what is the 100 there? 3 digits, 100 and 4. Using the 4 digits, you can represent 1 into 10 to the power 100. But if you represent in the fixed point number, you have to give after 1 there are 100 zeros. if you want to represent in the fixed point. So the number of the bits will be very large if I use a fixed point representation. Clear? So this is the advantage, very large, similarly very small. If I use a negative number sign bit, very small number you can represent, where it is very difficult in the fixed point. Now, what is the disadvantage? If it is the advantage, surely there is some disadvantage. Disadvantage is that circuit is complex. What type of circuit? Circuit for the arithmetic operation. It is very complex in case of the floating point representation. Clear? 6 points, we easily know how to add two numbers, how to make the division, but in the floating point, it is very difficult. It is not so easy. Clear? Now, the normalized floating point. What is normalized floating point? The definition of the normalized floating point is exactly one non-zero digit is to the left of the point. See the example, it will be clear. Suppose this is a floating point number. Okay, this is only a floating point number. But the second example is equal to, this is a normalized floating point number. Why normalized? Because to the left of the point, this is the decimal point, to the left of the point, exactly one non-zero. Non-zero here is the 2. That means 2.32 into 10 to the power 2. That is called the normalized floating point number. Okay, that means if I move the point here, the power will be decreased. Okay, so this is called normalized floating point. So here is another example of normalized representation. This is in the base 10, this is in the base 2. Suppose this is the number, this is a floating point number into 2 to the power 0 here. So this number, we have to make it a normalized floating point. What do we have to do? We have to move this point in the left hand side until we encounter one non-zero element. So first non-zero element we encountered here. After that, last non-zero element is 1. After that, all are 0. So we have to move the point here. Clear? So from left, we are moving the point here. So this is that is 1.01101101 into 2 to the power 5. Okay, if I multiply it to the 5, that means 1, 2, 3, 4, 5. The same number we will get. So this number is the normalized floating point representation. Clear? This is very important for the machine. Clear? So this is not normalized. This is normalized. This is not normalized. This is normalized floating point representation. Clear? Because only one, exactly one non-zero to the left of the binary point here. Clear? Any number for normalized floating point representation, you have to write in this way. Now, IEEE 754 representation. IEEE 754 representation is actually the representation of the floating point number. Clear? Now, what is IEEE 754? IEEE means Institute of Electrical and Electronics Engineers. What is the function of IEEE? You can find it that IEEE is an organization which actually standardizes different things which you use in the electronics or in the computer. Okay, they have also some research journals also. IEEE do many types of works. Okay, so they have given some fixed point representation. That means some standard fixed point representation. Standard floating point representation. Why this standardization is required? Remember that when floating point is used by the different machine, it is possible that different manufacturer use different floating point representation in their processor. Yeah, suppose there are two processors. One processor is made by the Intel, another is the Motorola. They use the floating point circuit, but their floating point representation is different. Clear? Some use normalized, some use non-normalized. Clear? Now problem is, suppose you are running a program, you are written a program for one processor. You want to try the run the program in another processor. But as their floating point representation is different, you may get different types of answer, or there is a problem in converting from one representation to another. So it is very difficult. For this reason, IEEE 754 gives some specification. They told that if you manufacture the machine, you have to follow this specification for making the floating point representation. Clear? And today's all the modern machines, they use the floating point representation. There are two types of floating point representation. One is the single precision. That means it contains 32 bits in the representation. and another is called the double precision. That means they contain 64 bits in the representation. Clear? Now, what is the 32-bit single precision? Today we will discuss about the 32-bit single precision number. In the 32-bit single precision number, here you can see here the left hand side 1 bit is for the sign. Sign bit means whether it is positive and negative. If it is positive, it will be 0. If it is negative, it will be 1. Clear? This is the 1 bit. Then comes the exponent. Here it use single precision 8-bit exponent. That means here the number of the bits will be 8. Clear? Then comes the mantissa part. Mantissa part is a 23-bit fraction. That means here m will be the 23 bits. So what is the IEEE 754 single precision? Sign bit is 1, exponent field is 8 bits, and mantissa field is 23 bits. Total you will get 32 bits. Clear? They are divided the system into this way. Clear? Now the question is how to represent any number into a IEEE 754 representation. Clear? See the example, it will be clear, and listen carefully. Clear? Suppose we have to represent one number to the IEEE 754 floating point representation. Clear? Now the thing is, suppose we have to convert this 228 number into IEEE 754. Clear? See the steps carefully. First, as the number floating point number is a binary, first step you have to convert the number into binary form. So here suppose 228, this is the decimal point base 10. We represent the number into the binary. Binary is 111001000. This is the binary. I have written here 2. That means that is the base is 2. Clear? So this number we have to represent it into normalized floating point number. Clear? To represent this number into normalized floating point number, see, point is here. We have to move it to the left. 1, 2, 3, 4, 5, 6, 7. Stop. Why? Because the left hand side of that bit is exactly one non-zero number. So this is a normalized bit. So we represent it as a 1.11011. We are not written the 0 here. No need. So this into, as we left the bit to the 7 positions, this is 2 to the power 7. So 228 is represented into the normalized floating point number. This is the first step for IEEE 754 representation. Clear? Now here you find out what is the sign bit. As the number 228 is a positive, obviously sign bit will be 0. Clear? Sign bit is 0. What is exponent here? Exponent here is the 7. Clear? This exponent here is the 7. Now, what is mantissa? Mantissa is this part 11011. Remember that in the IEEE 754, you don't have to give this one. Okay, you have to write the value which is after point. That means 0.11011. As this is normalized, machine will understand that there is a presence of one particular one before the point. So you write only the values after the point. That means 11011. So this is the mantissa. Clear? When we reverse it, we'll put 1 before this point. Clear? Add bias 127 to exponent. Why I am adding the bias, I will explain the next slide. Just remember that with this exponent, that means 7, any exponent, we have to add this bias 127. Clear? So the number is 134. If I add the bias, if I represent in the binary will be 100000110. So this is the representation of the exponent after adding the bias. Clear? Bias 127 you must add every time. For single precision, bias is 127. Clear? So IEEE 754 representation is now, you know, sign bit 0. This 0 is 0 here. Then comes the exponent. What is the exponent? 100000110. So in the red color, I have written the exponent, and the mantica 11001. 11001. After that, all the remaining bits, because this is 23 bits, you have written only 1, 2, 3, 4, 5 bits. All the remaining bits will be 0. Clear? So this total number is the IEEE 754 representation of the number 228. Clear? That means inside the machine represent, if you write 228, machine will represent the number in this form. This is a floating point number, and this is IEEE 754. Clear? So first, this is the IEEE 754 representation. Now question is the why bias. I have written here that we have to add the bias. Now the question is why bias is required. See here, the 8-bit numbers, I have already told the exponent is 8-bit. So 8-bit numbers is represented, we can represent it 0 to 255. You know that is 2 to the power 8, 256 numbers we can represent. If in the exponent we use one sign bit, that means number will be half. It will be minus 127 to plus 127, because we are halving the number, one half for the negative number, one half for the positive number, because we have to write the provision for both positive and negative. So we are dividing the number into minus 127 plus 127. Clear? But what is the problem with that? If I use sign bit here, this is called sign representation, and it comes from the minus 127 to plus 127. The problem is here 0 can be represented as 0 means 0, 0, 0. If I 0 here, that is the positive 0, and another is for the negative 0. So that is the problematic. The 0 can be represented two way, one positive and negative in this sign bit representation, though that is the problematic for the machine, because in that case the circuit will be complex. Clear? Because 2, 0, they are both equal. You have to understand the machine that both are equal, but they are the 0. Okay, but they are a positive 0 and negative 0. For this reason, we add the bias 127. Okay, so if I add bias 127, if all the numbers from 0 to 126 consider negative. Why? Because as the number is 0, okay, what is the actual number? Actual number is 0 minus 127 minus 127. See, this is the minus 127. And 126 minus 127, that means minus 1. Clear? That means minus 127 to minus 1, they are the negative number. 127 represents 0. Why 127 represents 0? Because 127 is actually 0 plus 127. We have add the bias here. So 127 represents 0. See here, there is no positive 0 and negative 0, simply 127. So that means actually 0, because we are adding 127 with the thing. And values greater than 127 is positive. Okay, that means if you, in the previous case, suppose in the previous case here, 127 we have added with the 7. Okay, so it is a positive number. If it is a minus 7, it will be minus 7 plus 127, it will be 126, and it will be a negative number. Okay, so if I want to add minus here, we have to minus 10 plus minus 7 plus 127. Okay, if number is a minus 50, so minus 50 plus 127. Every time you have to add the bias. Clear? Now question is, this is for the single precision. If I use the double precision number, what will be the bias? In the double precision number, the bias will be the 1023. Clear? So this is our bias floating point representation. Now the reverse representation. How to convert into opposite? If the IEEE 754 is given, how to convert it to the original number? Okay, this is the reverse representation. That means minus 1 to the power s is the sign bit, into 2 to the power y2, because IEEE 754 the number is actually binary. So 2 to the power e minus 127. Why minus 127 we are doing? Because 127 bias is we already added during the making of the floating point number. So we have to add this 127. And we know that mantisha part, we have only written the part after point. So we have to add 1 point this original mantisha. Okay, because for the floating point representation, we have given the number here. Okay. Now, how to convert the number? See here. Here I have given, see, this number, the previous number in the example, suppose this number is given. This is in the IEEE 754, it is given. Now here, so -1 to the power 0, sign bit here is 0. So this 0 comes here. So it is -1 to the power 0 into 2 to the power, this exponent part. Exponent part is this. This is the exponent part, and 1 into mantis 1 point m. M means that this is the mantissa part. So mantissa part is 11010. So this after 124 minus 127, this is 134, sorry, 134. So after pushing the number, so 2 to the power 134 minus 127, 1.000, because this is number is positive, 2 to the power 7 into this, we'll get, this is a normalized number, we get the original binary number, and from that, if I put it the decimal, we get the original decimal value. Clear? So this is our floating point representation. That's the reverse. Now here some special cases in the IEEE 754. The special case is, what is the special case? If the number, if the sign bit is any sign bit 0 or 1, and all the exponents are 0, all the mantissa are 0, this number is considered as a 0 in the IEEE 754. Similarly, if the sign bit is 0, all the exponent bits are 1, all the mantissa bits are 0, it will be considered as the plus infinity in the IEEE 754. Remember, this is the special types of number which is already fixed by the IEEE 754. Clear? Similarly, if the sign bit is 1 and exponent bits are all 1 and the mantissa are all 0, it will represent minus infinity. Clear? And if sign bit may be anything and the exponent, all the exponent bits are 1 and mantissa are non-zero, remember they should be non-zero, then it will be a nan. Nan means not a number. That means it may be the binary, it may be the imaginary number, suppose square root of -1. Clear? So this is the special cases of floating point representation in IEEE 754. So this is the last slide, and thank you. Now, if you have any question, you can ask. Unmute yourself and ask, and kindly give the attendance. Any question you can ask? Unmute yourself